Okay, hello everyone. In this video we will learn about metric spaces. So as I told you in the first class, for any of the basic necessities like open sets or closed sets or interior points or exterior points, or maybe the diameter of a set or a limit point, so all these terms to be defined you need a metric. So a metric is the one which establishes a space. It is the one which establishes the space. It is the one which establishes different kinds of sets, and it establishes different spaces, different kinds of sets, or different topology for that matter. So a metric always induces a topology if you have as you have already studied in the topological space. So let me walk along with you, or talk about definition of a metric. So this I definitely defined it in the very first class, but I'm doing it again. So a function d on m cross m satisfying the following properties is called a metric on M. So the first one, 0 is always less than or equal to d of x comma y is less than infinity. That is the metric of the functional value of d is always greater than or equal to 0. This is true for all the pairs x comma y belonging to M. And second one is, when is it equal to 0? So if and only if d of x comma y, if and only if the distance is measured between the same points, if and only if they are equal. Third, it is symmetric, so it doesn't matter the order in which you measure the distance, either from x to y or y to x, it is one and the same. Okay, this is true for all x comma y belongs to M. And fourth one is called the triangular property. D of x comma y is less than or equal to d of x comma z plus d of z comma y for all x, y, z belongs to M. Okay, so this is the definition of a metric. And sometimes a function will satisfy all the properties, but it doesn't satisfy number 2, and it is sometimes called as pseudometric. So if d satisfies all the properties except the second property here, so it is called as pseudometric. So all the terms that we defined, the open sets or neighborhood or limit points, we defined it in terms of sets, right? So we defined a neighborhood in terms of containment of a set or something like that. And even open sets, we defined it in terms of neighborhoods, which was defined again based on basic or general sets. Okay, so that we did in the first few sessions. But that those sets can, all the definitions can be established using a metric. So we will see how. Before that, let us go back to the examples. Okay, so there is a problem in the homework which asks you to check whether some of them are metric functions, or some functions are, is it a metric or not on a particular space. I think it's basically on real, as we are studying real analysis. Okay, so the very first and very simple example would be, every set will at least admit at least one metric. So for example, the function d of x comma y is equal to 1 for any x not equal to y in M. Okay, and so this is a basic metric that any function or any set will admit. So and d of x comma x is equal to 0. This is true for all x belongs to M. So this metric is this is a very basic metric, or a mundane metric, and it is always available, and this is called as discrete metric. So maybe if this is confusing you, you can write d of x comma y is equal to 0 if x is not equal to, is equal to y, sorry, if x is equal to y, and equal to 1 if x is not equal to y. So this is the same thing that's defined written in a different way. So this is very interesting metric, and it is a set applied with this metric, discrete metric, is called as discrete space. So a set applied with this metric is called as discrete space. So you would have studied discrete space in topology, discrete topology, wherein the only two open sets are the null set and the set itself. So this particular metric actually establishes that topology. So another important example on the real line would be the metric defined as d of a comma b is equal to absolute value of a minus b. So this is you can check this whether this is a metric or not by checking all the 4 properties. Okay, so this is any time if we refer to R and without explicitly naming the metric, so this would be the metric that we will be referring to, and it is called as the usual metric on R. Okay, so and any subset of a metric space is again a metric space, and this is in a natural way. So if D is a metric on M and if A is a subset of M, then d of x comma y is defined for any pair of points x comma y belongs to A. So D, when restricted to A cross A, it will definitely satisfy all the 4 properties. Okay, so that is so that means to say that if A is a subset of M and there is already a metric that is defined on A, okay, sorry, M. If D is a metric defined on M already, it would definitely satisfy the properties on A and even on the Cartesian product of A, like A cross A2. Okay. So for example, a very particular interest would be N and Z and R mod Q. R mod Q is set of all irrational numbers. So each of these sets will already come with supplied with are already supplied with a natural metric, which is called as the usual metric on R. So that is the example B here. So all these sets would carry the usual metric on R. Okay, so this would that means for all these sets, the restriction of this particular D here, the usual metric on R, works. Okay. Okay. So now in some of the homework problems, I have given some questions on metric spaces. I'm sorry. Okay, I have given some questions on metric spaces. Oh, sorry, norm spaces. So I think it would be better if I define a norm on a vector space. So okay, definition: a norm on a vector space V is a function which is denoted like this: from V to 0 to infinity. Again, this is nothing but metric again. So you will see that is a part of your homework problem. So to prove that every norm induces a metric, okay, so satisfying certain conditions. First one, 0 is less than or equal to norm x less than infinity for all x belongs to V. Second, norm x is equal to 0 if and only if x is equal to 0, and it's a vector. This is the 0 vector in V. Okay, so third, norm alpha x is equal to absolute value of alpha norm x, where alpha is a scalar for any scalar alpha and vector x. Okay, so and then fourth would be the triangle inequality again. Norm x plus y is less than or equal to norm x plus norm y. So if any function from V to closed, semi-closed, 0, infinity, if it satisfies all the four properties, then it is called as a norm. And again, even here, if a function satisfies all the four properties except the second property here, this property, it is called as pseudonorm on V. So same as that of a metric. And this function along with the vector space would be called as V along with the specific norm is called as normed vector space, or they say norm linear space. That's fine. It is called as norm vector space, and it is easy to see that any norm will induce a metric on V. So just like you have the discrete metric, that is obvious metric, so there is an obvious norm also. So that would be D of this norm will induce a metric which is norm x minus y. So this is a norm, this is any norm will induce a metric on V, which is set in this way, in this manner. And this is usually referred to as usual metric on any vector space. Or any normed vector space. Okay. uh, so for example, uh, first one, any absolute value function will definitely define a norm. So the absolute value function is a norm, example of norm. Okay, and second example, one norm which is usually defined as, usually we use norm to be a metric that is defined on a dimension of a space more than more than like not real line. So I real for real line you will have absolute value. So if it is R2, R3 or more than one dimensional space, you definitely use norm. Okay, so what is a one norm? One norm would be the distance of the point from the origin. Okay, so distance of the point from the origin, which is defined as summation I is equal to 1 to n absolute value of xi. Okay, so and 2 norm is defined to be summation I is equal to 1 to n absolute value of xi square whole to the power of half. So here 2 and 2 cannot cancel because you have the summation of the squares and the square root. Okay, and infinity norm is defined to be max of 1 less than or equal to I less than or equal to n absolute value of xi. So where all these xi's, what are these xi's? They are nothing but the terms of an n tuple, coordinates of an n tuple. So where xi's are nothing but coordinates of an n tuple x, which is nothing but one point in Rn. Okay, so the first and the last expression, this and this expression are very easy to check whether it's a norm or not. And the function norm 2, that is norm 2 norm, here this is called as Euclidean norm. Okay, this is called as Euclidean norm, and it is generally accepted as a norm of choice on Rn also. And for any 1 less than or equal to p less than infinity, so the expression p norm would be defined as summation I is equal to 1 to n xi to the power of p whole to the power of 1 over p. So this defines a norm on Rn. Okay, so another important example, so that will be helpful for your homeworks. Third, suppose you have, I will take you back to this particular set here. So this is the set of all continuous functions on closed interval a comma b. So this is the set of all continuous functions. So the elements here are nothing but continuous functions. So how do you define the norm between, how do you measure the distance between two functions? So that is norm 1 of f is defined to be, where f is a continuous function on closed interval a comma b, is defined to be integral of absolute value of f of t dt. Okay, and norm 2 would be defined as integral a to b absolute value of f of t square dt whole to the power of 1 of 1 by 2. So for terms to be added, you can definitely add the terms. And what do you do for a function? What do you mean by like adding a function? It is nothing but integral. Integral represents the summation. Summation, and for a function the summation would be nothing but an area of the curve under area of the curve sweep through with respect to a particular axis. So this is, so you can try to relate the terms, norm of the terms defined, Euclidean norms defined to the norm being defined on the set of all functions. So going in this manner, f infinity would be defined to be max of or they take, you can take even the supremum value, or generally they take a maximum value. So again, the second expression here would be the hardest to check. Okay, and the last expression is generally taken as the norm on, this expression is generally taken as the norm on the set C of closed interval a comma b. So next example would be normed vector space. So if V is a vector space, so what there we defined it to be a subset, like matrix was defined on a subset. So what would be the role of a subset kind of a thing, a relation subset with respect to a vector space? It would be a subspace, correct? So if W is a linear subspace, and you already have a norm defined on the superspace here, so the same norm can be applied to W2. So the restriction works, the restriction of the particular norm defined on V to W definitely works for W. It's definitely a norm on W. Okay, so fifth example would be so we might also consider the sequence space analogues of the scale of norms on Rn. So something like that is given in B. For example, 1 less than or equal to p less than infinity. We define LP to be the collection of all real sequences. So collection of all real sequences, LP space. So for which the norm is defined to be collection of all real sequences satisfying the condition summation I is equal to 1 to n absolute value of xn p is less than infinity. It's a finite number. The summation of each term raised to the power of p would be a finite number. So less than infinity means it is a finite number. And again we define L infinity. So maybe if now I am defining L infinity, maybe you can go back and work on the C0 problem that was in the homework 1. Okay, so L infinity is defined to be a collection of all bounded real sequences. Collection of all bounded real sequences is said to be L infinity, and LP is all the sequences which satisfy this condition. Okay, so next moreover the expression norm xp is nothing but as defined earlier, xp would be xn summation of all the uh, terms xn to the power of p whole to the power of 1 over p, where p is nothing but takes the values from 1 and 1 from and 1 to up to infinity, and for x infinity it would be sup n absolute value of xn. So if p is infinity, so this defines a norm on LP. So the cases p is equal to 1 and p is equal to infinity. So this is the norm defined on LP for p is equal to 1 and p is equal to infinity. So that is very easy to check. You can work on that. So and the case p is equal to 2 requires a special attention, and that the proof of that you can find it in any book. And there are certain properties that is associated with all these norms. They are like there are certain theorems like the Cauchy squares inequality. So you might have learnt all that in functional analysis, and you may have to go through all of them again. To refresh your some of the properties like the Minkowski's inequality, Holder's inequality, Cauchy squares inequality, and stuff like that. So if you have to solve the homework problems, so I have made sure that I don't give any of the homework problems which I have not explained or which takes extra effort. But still, if you find something that you are dealing out of the context of things that has already been taught to you, go back to the textbooks, especially Carruthers and Carruthers, Rudin and Wade, that I will be mailing soon to you guys. So you go back to them and look for the definition, look for the ideas. You will definitely be able to solve them. So I will end this video here, and for the next of the video, in the next video we will define all the terms like the open ball, boundedness, closed ball, and close how do you, diameter, etc., that you will be using in the homeworks again. So all those that things that you generally define on sets can be defined based on using a metric. So we will be doing that in the next video.